Hello, welcome to my talk on Newton's binomial series. As generally accepted, Newton is one of the greatest mathematicians in history. In addition to his key role in the scientific revolution in mechanics, some might say Newton is one of four greatest mathematicians in the history, with the other three being Archimedes, Euler, and Gauss. Newton's most important contribution in mathematics would be the invention of calculus. It should be noted, Newton invented calculus based on the previous development, as well as his binomial series. In today's mathematics, his binomial series has been replaced by the easier and more generalized series, the Taylor series. This is why we hardly see the applications of the binomial series anymore. However, to make an introduction how Newton brought out his calculus, his binomial series is a must, and we'll see why his binomial series is so important. In this talk, I will talk about what is the Newton's binomial series, why Newton's binomial series is so important in terms of the calculus invention, how to use the Newton's binomial series for the normal binomial function, and use Newton's binomial series for some generalized binomial functions. Nowadays, binomial series is not used anymore. Instead, we can now use the easier and better Taylor series. But we must note, Taylor series is based on calculus, while the Newton's binomial series was proposed before the establishment of calculus. And in introducing how Newton invented calculus, the binomial series is a key factor. In my serious talk on this topic, I am targeting to draw out the Newton's calculus in a more logical manner. As we have learned in secondary schools, or some even in the primary schools, the conventional binomial function would be given as this. And here we can see the exponent number is a positive integer. And the Newton's binomial series is for the more generalized binomial function, given in a general form as this. And the expansion of this binomial function in this form. Here, each of A, B, C, D represent the previous term, and M and N can be any integers, could be positive and negative. For instance, if we take P equaling to 1, Q equaling to minus x, and M equaling to minus 1, and it's 1, then we have the binomial function given in this. If we take P, Q, M, and N, so we have the binomial function as this. Again, if we take a different P, Q, and M equaling to minus 1 and equaling to 2, so we have the binomial function as this. And we can have more complicated binomial functions. Isaac Newton was a mathematician, physicist, astronomer, theologian and a natural philosopher who is widely regarded as one of the most influential scientists of all time and a key figure in the scientific revolution. Newton is one of the greatest mathematicians in the history. As a mathematician, Newton is famous for his invention of calculus. For his invention of calculus, his formulation on the generalized binomial series should be very important, since without it, Newton could not invent his calculus. Newton's binomial series could provide the expansions or series for the generalized binomial functions. It could create the base for Newton to invent calculus and let Newton to perform the interesting inverting of infinite series. Allow Newton to perform the integral calculation, more specifically the area calculation under a curve. Suggest Taylor to follow the similar idea to expand the arbitrary function into infinite power series, the famous Taylor series, which we are using today. It is simpler and more useful. I have tried to find out how Newton obtained or derived such an expression for the infinite series, but unfortunately, I didn't find the relevant information, and I reckon Newton might have no strict mathematical derivation for this expression. Newton could have used the trial and error method to find the expression. His deduction skills and the intuition would be very important in developing the expression, as we can see some simple examples in this talk. In this slide, I will make a simple comparison for the conventional binomial function and the Newton's binomial function. The conventional binomial function is the simple binomial function. For instance, we take m equaling to p equaling to 1 and q equaling to x and n equaling to 1. So we have the binomial function 1 plus x squared. So we have the expression for this. And if we take m equaling to 3, we have the expression as this. And so on, we can have more different conventional binomial functions. So all these functions have a common feature. They have finite terms in the expression. However, for Newton's binomial function, the integers m and n can be any value. Both can be positive and negative. A very simple example is m equaling to minus 1, n equaling to 1, p is 1, q is minus x. So the expression can be expressed as the infinite power series given in this form. In this regard, the Newton's binomial function can have infinite terms. To show the applicability of the Newton's binomial series, a basic form given in here. Now in this slide, I will use Newton's binomial series for the cubic binomial function. Here, p equaling 1, q equaling to x, m equaling to 3, n is 1. So we have the binomial function as this. Using the Newton's binomial function, the first term we calculate as this. It is 1. So we can obtain a equaling to 1. Then we can calculate the second term given as this. So we can obtain the second term as 3x. So we can have b equaling to 3x. Similarly, in the third term, we use the value m, n, b, and q. So we can obtain the expression for third term. It is 3x squared. Therefore, c is 3x squared. For the fourth term, we can use all this known value m, n, c, q. So we calculate the expression for the fourth term. That is x cubic. So we have d equaling to x cubic. And the fifth term we calculate as this, and we find the fifth term is 0. Therefore, e would be 0. But we can stop here, since if we go on to calculate more terms, it will be all 0. Therefore, if we put all these terms together, we have the expression given as this. So this is exactly same as we have learned in school. In this slide, we will apply the Newton's binomial series to a simple generalized binomial function. Here, p equaling to 1, q equaling to minus x, m is minus 1, n is 1. So the binomial function is given as this. So the first term is calculated as this. It is 1. So we can get a equaling to 1. The second term, we can apply the values for m, n, a, and q. So we obtain the second term, x. So b equaling to x. The third term is calculated as this, and it is x squared. So we have c equaling to x squared. The fourth term is calculated as this, so we obtain x cubic. So d is x cubic. And the fifth term, we obtain the expression as x power 4. So we can go on to calculate more terms. But now we can already see the pattern of the binomial series. Therefore, if we put all the binomial series together, we can get the expression for this binomial function as this. And we have seen in many places this is correct for the binomial series. Here in this slide, a discussion would be made for this simple binomial series, and we will see how this problem can be simply solved. As we see, this is an infinite geometric series, so we use capital S to represent the value of the series. The next step is to group some terms together, see here, and then we take x out of this group, the bracket. So we can see in the brackets we construct a new geometric series. Therefore, if we use capital S to represent the series, we have the expression as this. So we can solve the equation and we obtain the series S given by the expression as this. So this geometric series is given by this expression, or we say this binomial function can be expanded into an infinite series as this. It should be noted, for this geometric series, we should limit x, that is, the absolute x is smaller than 1. Otherwise, the geometric series would be divergent. And for a divergent series, we should not able to make the mathematical derivation in here. So if you are interested why this is the case, you can watch my talk on mathematical tricks on harmonic series, and we will see more information on this limit. The absolute of x is smaller than 1 for this geometric series. A further discussion on this geometric series is given in here. Now we consider only the limit terms of the series given by this. So we have capital M plus 1 terms for the series, and the value is indicated by Sn. As we have done before, we group these terms together and then take x out of this bracket. So we have a new finite series, but this is slightly different from what we start in here. And we see this series and this series, the only difference is the last term x power of n. So we can express this new series as Sn minus x power of n, given as this. So we can build the equation for this finite series as this, and we solve the equation, we can obtain Sn given in this expression. In here, because of the series is finite, so there will be always a certain value for this Sn. Hence, for this mathematical derivation, there's no limit for x. That means x can be any value. Smaller than 1 or larger than 1 is always correct. The only thing is when x equaling to 1, we need to be careful for this calculation. As a special application for this series, we now consider n is infinite. So we can see from this expression, if n is infinite, Sn would be only finite when absolute x is smaller than 1, such that the limit of x power of n plus 1 would be 0 when n is infinite. As such, we have the expression s equaling the limit Sn when n is infinite. So we have the expression. So again, we see the expression s equaling this is only for absolute x less than 1. The next example is a more difficult binomial function. Here, p equaling to 1, q equaling to minus x squared, m is minus 1, n is 2. So the binomial function is given as this. So use the Newton's binomial series. The first term is calculated as this. It is 1 and a equaling to 1. The second term is calculated as this. It is half x squared. Hence b is half x squared. The third term we calculated as this. So it is 3 over 8 x power of 4. So c is given as this. And we can calculate the first term given as this, d here. the fifth term given as this. E is this. For this binomial series, we can go on to calculate more terms, but for many practical applications, we might not need to go for too many terms. So if we put all this together, we have the expression for the binomial series given as this. So this binomial series is much more complicated than the previous example. And we may ask a question, is this expansion is correct? Or how we can prove its correctness? In this slide, we are going to use a very simple way to examine whether the binomial series is correct or not. The way we prove it is term the binomial function by itself and the binomial series by itself given as this. So we put all these terms of the same order of x powers. So the first term would be 1, and the second term in this bracket, it would be the x squared. So we have half plus half. And in this bracket, we have the order of x power of 4. So we have here 3 over 8 and here 3 over 8. And then this half x squared times half x squared. So all these terms will have the same order of x power of 4. And this term we have x power of 6. So if we calculate this, we can find a very simple expression for all these terms. That means we have the expression as this. Obviously, this binomial function and this binomial series is correct.